Hello.
Hello, hi.
Hi.
How are you?
Good, thank
Good,
you.
thank you. Okay, so what we did last time? What we did last time?
Oh, we about the kinematic equations and like resistance and stuff. And we talked about like series and parallel circuits and um the current and like the voltage in a series and
Okay,
parallel.
fine. We done the series and parallel combinations. Okay, let me check once. Okay, fine. So the last class we were talking about the current electricity, right?
Yeah.
Okay. So we started with the definition of electric current, and then we talked about the potential difference, direction of current, motion of electrons, the components like batteries, resistors, switches, voltmeters, ammeter. Then we also explained about the series and the parallel combinations, the how the current and the voltage gets distributed in them. We
Yeah.
also have seen that equation between the voltage and the current is like V is equal to I times R. We call it the Ohm's law. And at the end, we were talking about the different types of register, like the difference between the fixed and the variable register. And then after then, we talked about the conversion of yeah, we talked about the potentiometer. Okay, so this is what we did so far, right? Hmm. So what's the definition of current?
It's the rate of flow of charge.
It's a rate of flow of charge. Okay. And how do you define the potential difference?
It's like voltage. It's like the push on the electrons in the circuit.
What's the formula?
V is I over R. Or
V is
I
I,
times R, sorry.
I times R. What's I? What's R?
I is um I is current and R is resistance.
I is current, R is the resistance. Okay. So can I say that if the potential difference is more, the current is also going to be more?
Yeah,
Okay. And that's what we call the Ohm's law, right?
yeah.
Okay. How do you define the... Okay, if you have a series combination or a parallel combination, how do you differentiate the two?
In series it's one singular path all the way around, and in parallel it splits into different paths. And also for series, the current stays the same everywhere, and the voltage gets split, and in parallel it's the opposite. So the current is different and the voltage is the same.
Okay, and fine. So Which circuit do you prefer? Do you prefer to be having a series or a parallel circuit?
Like in real life.
Yeah, in real life.
Um,
More convenient,
parallel,
better way. And why do you say that?
parallel, because we can have like different components, and even if one component fails, then the rest will still work. So we don't need all of them. Like you can have one that stops working, but the rest will still function. But in series, if one of them stops working, then everything in that um in that in
Mm-hmm.
that like circuit stops working.
Okay, makes sense. Fine. And how do you measure the current in the circuit?
Um,
Is there any
with an
instrument?
ammeter
And how do we connect the ammeter in series or parallel?
in series
And how to measure the voltage
with a voltmeter in parallel.
with a voltmeter in parallel across the register, right?
Yeah.
Okay, makes sense. Um, Fine. So if let's say three registers are given, all the three of them are in series, how do you find the total or equivalent resistance of that circuit?
Sorry, three. Sorry, can you repeat the question?
There are three registers,
Yeah.
all of them are all of them are in series.
Yeah.
What's the total resistance?
Oh, it's just R1 plus R2 plus R3.
And what if you have all the three of them in parallel?
It's 1 over R1 plus 1 over R2 plus 1 over R3 is equal to 1 over total resistance.
Okay, so first you solve it and then you have to flip the answer, right?
Yeah.
Okay, makes sense. What's the difference between a fixed register and a variable register?
A variable resistor is like a rheostat. For example, there's like something on top and you're able to move it to like control the amount of resistance that like it's giving. But for a fixed resistor, like the resistance is fixed and you can't change it. It's like a specific amount.
It's like a slider on top of it, right?
Yeah.
So we can, as we move the slider, we can change its values, right?
Yeah.
Okay, makes sense. What is potentiometer?
It's a three-terminal resistor.
Mm-hmm.
Where it's like a variable resistor where you're able to like change the amount of resistance and stuff.
Okay. Mm. What's the difference between a cell and a battery?
A battery is like multiple cells. So one cell is like one singular part of it, and a battery can be like
The
more than one.
combination of the cells, right? Okay. The group of cells together called the battery, right? Hmm. So, for example, on one side we have the direction of current. On the other side, I'm having the direction of electrons. How these two directions are different? Are these the same direction, or they're representing the other some other directions?
Wait, does it have to do with the conventional current and the real current?
So, what's the direction of conventional current,
It's positive to negative,
and what's the direction of electrons?
negative to positive.
Okay, when I say the current is flowing in a circuit, is it like the electrons are moving, protons are moving, or the neutrons are moving?
The electrons.
So there's no protons motion, right?
Yeah.
Why not the protons and neutrons? Why only the electrons move?
Because the electrons are negative, right? So they are like attracted to the positive side.
No, but that way proton is positive. It can get attracted towards the negative terminal.
Um,
Why not proton? What's so specific about the electrons?
because the electrons carry the charge.
No, again, I'm saying the proton also have the charge.
Um,
Okay, tell me one thing. How does an atom look like? What is inside the nucleus and what is outside it?
The electrons are outside it, right?
The electrons are outside. Okay, what's inside the nucleus?
The neutrons
Yeah, electrons. Yes, and anything
and
else?
the protons.
The neutrons and the protons, right? And both the protons and neutrons are attracted by a very strong nuclear force. So they are not allowed to move. When they are inside the nucleus, they are highly attracted towards each other because of the strong attraction. But when I'm talking about the electrons are free to move. The moment they get the opposite terminal, like positive terminal, they start moving towards that. So the electrons are free to move. Protons are not allowed because they're highly attracted inside
Oh,
the nucleus. Okay, they're not allowed to move. The same thing happens with the neutrons also. Correct?
yeah.
And also the electrons, it's not like all the electrons are allowed to move. Only the electrons which are in the excited state. Okay, it's not like the ground state electrons are moving. That's not the case. Correct?
Yeah.
Okay, perfect. Um, what's the unit of current?
Amps.
The unit of current is amperes or amps. Okay, how about the potential?
Voltage.
Yeah.
So volts.
Okay, voltage or volts. Okay, fine. Um, how about resistance?
Ohms.
Okay, and how does the symbol look like for
It's like it's like an open circle with like two lines.
yeah, correct, exactly. Hmm. If we draw the graph between potential and the current, how does the graph look like? If I put the potential on one axis, the vertical axis, and the current on the horizontal axis, how does the graph look like?
Would it be a positive correlation? Like it would go upwards?
Is it like a positive? Okay, it will be positive. Okay, but will that be a straight line, curved path, parabolic? How does it look like?
Is it straight line? Because
Because
this resistance is staying the same. So the current is like going up and like is like proportional to the
yes, that's correct. Like
volts.
if it's three, V is proportional to I. That's what we learned, right? Now, when I'm saying V is proportional to I, that means let's clearly say that if V is proportional to I, if I increases, V also increases. So that has to be a straight line. And the slope of this line will give you the resistance. Okay, I'm repeating again. If you draw the graph between V and I, the graph for conductors, that graph is going to be a straight line passing from the origin. And if you find the slope of this line, that will give you the resistance. Got it? Perfect. Hmm. What's the difference between the conductors and insulators?
A conductor is like it's like helping the um the circuit or like making it go faster, but the insulator is slowing it down basically. Like it's a resistor kind of.
So can I say that anything that allows the electrons to flow through them are conductors, which doesn't allow the current to flow through them are the insulators, right?
Yeah.
Can you give me an example?
An insulator would be like rubber
Hmm.
and a conductor would be like magnesium.
How about the metals?
Sorry?
How about metals?
Like all metals, like magnesium, aluminum.
Everything is conductor?
Yeah.
Okay. And which is the strongest conductive
I'm
metal?
not sure. Is it aluminum?
It's silver.
Oh, okay.
Okay, so it's silver, and then after that we can say it's copper. Okay, that's
Okay.
why, like, if you look at the connections, all the circuits that we have in our houses, they're all copper wires, right?
Oh, okay. Yeah.
Okay, we cannot go for silver because it's quite expensive. So the next best option is using copper wires, or maybe the third option you can go for aluminum wires. Okay, perfect. What is EMF?
Sorry, E and F?
EMF, electromotive force.
I'm not sure.
Okay. Have you written the definition of volts in the last class?
Uh, I don't think so.
We not done that?
I don't think so.
Okay, then we have to write this one today. So we have two definitions that we have to. So there are two terms. One is voltage or the volts, and one is EMF. Okay. So let's see what's the difference in the two. Mm, Let me share the whiteboard. Okay, can you see the whiteboard?
Not yet. Yeah, I can see it now.
Okay, perfect. Write down the first heading. So I will be doing this in terms of a table. Let's have a look at this. So write down the heading, difference between the potential difference. We also call it the voltage. So either you can say that potential difference, or you can also say that the voltage and EMF and EMF. So what is EMF? We'll come to that. The first thing, on one side, I'm writing down the potential difference or the voltage. In short, you can also write it as PD, short, okay? Or it's also called as the voltage. And on the other side, I'm writing down electromotive force, electromotive force or EMF, EMF. The first classification, I'm talking about the definition of it or the meaning of it. When I'm talking about the potential difference, it's defined as the energy transferred. It's the energy transferred by a component, by a component per unit charge, per unit charge. And the second on the EMF, it's the energy supplied by the cell, energy supplied by the cell per unit charge, per unit charge. Now, that's a very important difference. Now, if you look at the definitions, it almost seems like same. Energy per unit charge. Here also energy per unit charge. But on one side, it's a transferred or delivered. On the other side, it's supplied. That's the two differences. I give you with an
Okay.
example. I explain you with an example. Let's say, for example, let's say for your you got, let's say, $100 from your parents, and they said, okay, you can just go and buy some gift for you, but you have to buy something for maybe something good for the family, maybe something important. So you bought something like $70. You bought something good, like which can be used by the family, and $30 you spend on yourself. Okay, now just look at this, the difference here. The 100 was given to you. Out of that, you only use $70, which was which can be used to the other members of the family, and $30 is occupied by you. Right. Now, what has been given to you is your EMF. What is what you have used for the family after taking your part, that is potential difference. Got it? So, for
Okay.
example, if there is a battery, the battery can supply a voltage of 100 volts. But when the current passes through it, the battery itself takes some of the voltage. Let's say 20 volt is taken by battery itself. So now what is left for the other parts? It's only 80, right?
Yeah.
Correct. So what is given to the others is the potential difference. And what was given by the battery, it's EMF. Now the question is why the battery is taking the energy. See, if anything has to work, it will require some energy. Even if the battery has to work, it will require some energy, right?
Yeah.
Correct. So, for example, let's say I consume 1,000 calories in a day. So maybe 500 calories is the energy required by my body itself. Maybe in the process of breathing, maybe in terms of doing the small task, right? I require my body also have some requirement, and after that, whatever is left over that I can use for anything else. So the requirement after taking my own requirement, whatever is left is your potential difference, and what actually is supplied to the system is your EMF. For example, let's say you go to the market and you buy a battery. On the battery, let's say this is a small battery like a pencil cell or something like that. On the battery, it's written as 5 volts. But in reality, when you connect with the circuit, it's not giving you 5 volts. It's only giving you, let's say, 4 volts. So the question is, where is that 1 volt? So that 1 volt is taken by the battery itself in order to function. Correct. So what is available to the others? Only 4. It's not 5. So this is what? This is your EMF. And this is what? This is your potential difference. That's actually delivered to the other components. Do you understand the difference now?
Okay.
Got it? So who is this
Yeah.
important for you? Is it the EMF or the potential difference? Like what others
Sorry,
are
I
going
didn't
to
catch
get?
that.
Like what others are going to get, that matters the most, right? If you're going to consume something by yourself, others are not getting that, right? So even while doing any calculations, if the EMF is given to you, you cannot take that. You have to take the its own voltage contribution out of that, and whatever leftover is given to the circuit. So that's important for us. Is that clear to you?
Okay. Yeah.
Okay. So that's the definition that we can see here. The second thing is, but if you look at the definition, there is no change. It's a work done per unit charge, work done per unit charge. How do you, hello?
Sorry, I got disconnected. I don't know why.
It's fine. So that's the difference number. That's the point number one. Point number two, let's talk about the symbol. We represent the
Wait,
potential. Sorry.
just like one question. For the example that you gave with the 5 volts and the 4 volts, so what exactly, like what number would be the potential difference and what would be the electromagnetic?
4, 4 volts is your potential difference. and 5 volts is the EMF,
Okay.
right? So even if you have $100, you're not spending $100 on the family. So for others, $100 is not the actual amount. You're consuming $30 by yourself. So for the others, it's only $70, right? So potential
Yeah.
difference would be 70 and the EMF would be 100. What's given to you and what
Okay.
you're spending on the others, these are two different things. Okay?
Okay.
So for the symbol for the potential difference is V, and for the battery, it's E. Now, talking about the formula, there is no change in the formula. The formula looks exactly the same. Here, it's also work done per unit charge, and here also the EMF is work done per unit charge. Point number four, both have the same unit. This is also measured in the volts, and this is also measured in the volts. There's no difference in that. The number five is the measured across. So where do we measure them? It's measured across the components like it's measured across components like registers, bulb, or maybe a motor. While on the other side, we find the EMF across a cell or a battery along the battery. Is that okay?
Yeah.
How do we measure them? The instrument is still the same. How do we measure it? We measure them. It's measured by the voltmeter. It's measured by the voltmeter. What's the function of each? So as I already explained, the function is, so voltage means the energy that has been supplied. It measures the energy that has been used. Measure the energy that has been used. While on the other side, it's measure the energy supplied. It measured the energy supplied by the battery. Okay. Um, how do we find that? So if I want to find, let's take an example. The example can be if I find the voltage across a resistor or maybe a lamp, a voltage across a lamp is your potential difference. But if you find the voltage across a battery, it's EMF. Voltage across a battery. That's your EMF. Okay,
Yeah.
perfect. Now, can you explain that again?
Okay, so basically, voltage is how much the energy is actually being used by the component. So since components take amounts like of voltage, like in a circuit, is given a specific amount of voltage, but each component takes some of the voltage. So like the potential difference is how much each component actually receives. But
Mhm.
the EMF is how much is like meant to be there. Like it's like the energy that was like given to it or
Given
like
whom? Given by
supplied
whom?
to it
Who's
to the
supplying that?
component by the battery.
By the battery. Okay, just tell me one thing. For example, the one example we have taken earlier, we said that on a battery it's written 5 volts. But when you look at the circuit, it's only 4 volts coming is the supplied energy, only 4 volts. So where that 1 volt is going?
To the battery, like the battery is
Yes.
using it.
Yes, the battery itself have to use some of the energy. So that's the 1 volt is going there.
Yeah.
And why do we use that? Even if I give you a better idea, how if you look at a battery, have you seen a battery from inside? How does it look like?
No.
So let's say, for example, if you have a small battery and if you cut it from like from the middle, you see that there are chemicals inside it, right? There can be like
Yeah.
so what these chemicals are. So when the electrons or the ions, when they have to travel through those chemicals, so what does a battery do? It converts chemical energy into electrical energy, right? So these chemicals, when the electron wants to pass from one electrode to the another, it has to pass through that electrodes, right? Through those chemicals. So in order to travel that distance from one electrode to another, from positive to negative, inside the battery, they have to do some work. And that work is the work done or taken by the battery. Okay, so out of 5 volts, one is taken by the battery itself. We call it as the internal resistance. Got it?
Yeah.
That's the internal resistance. I hope that was clear now.
Yeah.
Okay, perfect. Um, have you written the definition of resistance in the last class?
Yeah. It's the opposition to the flow of electric current.
Okay, we did that. Right. Okay, have you talked about the dependence of resistance on the length and the area of cross section?
I don't think
Okay,
so.
we're not done that. Okay, fine. Let's write down the next heading. Uh, Resistance and its dependence and its dependence. Let's say, for example, I have a wire. This is how a wire look like. It's having a length L. The area of cross section is A. Um, this is how it look like. So, what do you think? If it's a longer wire, if the wire is very long, will it have more resistance or less resistance?
Um, More resistance.
Yes, definitely. It has to travel a long distance, so it will
Yeah.
experience more, obstacles in the path. Can I say that would be proportional to the length?
Yeah.
Okay. Now, how about the area of cross section? Like the area of cross, I mean, the thickness of this wire. How about that?
Less resistance with more.
Okay, definitely. Like if it's a more area, it has more space to go, right? So the
Yeah.
relation would be inverse of it. Agree?
Yeah.
So when you write the two statements together, am I getting R is equal to L over A, right? And when you remove the sign of proportionality, you got a constant. We call it as the rho or resistivity. So here, this R is your resistance. We measure that in ohms. L is the length of the conductor. The length of conductor, we measure that in meters. And A is the area of cross section. A is the area of cross section, which is in meters square. Okay. So now what is this rho? Rho is called as the resistivity. Rho is called as the resistivity. And it has a unit of ohm meters. Okay.
Yeah.
Just write this down. Write this down. Is it done?
Yeah.
Okay, can you explain that?
Okay, basically, the resistance is proportional to the length of the conductor because the more length there is, the more obstacles and things there is in their way to pass it. And the area of the cross section is like the thicker or like the bigger the diameter of the of it like that it is, the less resistance there is because it's like easier to go through. Um so that's why it's like if it's like
Mm-hmm.
I don't really
So,
know. Um,
yeah, tell me. Explain that again. No worries.
I
So,
don't know how to like put it into words.
okay, can I say that on increasing the length, the resistance is going to increase?
Yeah.
Okay, definitely. I mean, if it's a
Yeah.
longer wire, it will have to travel longer distance, more obstacles in the path, right? So
Yeah.
more resistance. While on the other side, it's inversely proportional to the area of cross section. That means if the wire is thin, it will have more resistance. And if the wire is thick, it will experience lesser resistance, right? And this
Yeah.
constant is called as the resistivity. Fair enough?
Yeah.
Now, okay, now you have the formula with you. Now tell me, my question is, if the length and area of cross section is doubled, what will be the change in the resistance? What will be the change in resistance?
There's no change, right?
And why do you say that?
Because like for that equation thing, it would just be R is like 2L over 2A and you could just cross out the twos. So it's the same.
That's what you mean?
Yeah.
Okay, perfect. Okay, now the next part of the question. If the length doubles, if length doubles and the diameter of wire, the diameter of wire becomes half, what will be the new resistance? If the length doubles and diameter of the wires become half, what will be the new resistance?
It'll be 4 times the original resistance.
Hmm. Can you try that again?
Wait, it would be
It's see,
2L.
listen. It's a diameter. It's not. I'm not talking about the area. I'm talking about the diameter.
Oh,
What's the
oh,
cross-section area in terms of diameter?
oh. Pi 2 pi r.
That's
Oh
a
no, two.
circumference. The area is pi r square.
Yeah,
Okay, so what's the diameter? What's the area in terms of diameter? Okay, let me write down. So area, you're saying it's pi r square. And what's the
yeah.
relation
So
between the radius and the diameter?
radius is like 1/2 of the diameter. So it
Okay,
would be pi 1/2 of diameter squared.
yes, exactly. And how much is that? Is it
Um,
pi d square over 4?
yeah,
Okay, I got the area now. Let me just plug in the numbers. So the resistance is rho. The length is, you said the question says the length is doubled, right? And the area
yeah.
of cross section is pi over 4. The diameter is also double. Make sense?
Ye, ye.
Okay.
Wait, I thought the diameter is half.
You took the diameter as half, but isn't that the square of 2 would be 4?
Wait, but how come you make it 2D on the side?
Okay. The question says that the diameter's got, oh wait, the diameter is half. Wait. I written this wrong. I made it double. The question says the diameter is getting half. Okay, is that okay now?
Yeah.
Okay, perfect. So earlier it was
Wait,
point.
wait. I thought it would be like it would just be d squared because we already halved it on the left, right?
It's fine, it's fine. Let me just do it this way. You're saying that
Oh,
it's proportional to the length and square of the diameter, and we already made it half, correct?
mhm.
That's what you said?
Yeah.
Okay. So you're just doing the half of the diameter. So we got twice of length, the square of diameter, and the square of 2 would be 4. This force comes in the top. So what we get? We got it's proportional to the length times of d square, and 4 times 2 would be 8. So your resistance is going to be 8 times more compared to your original resistance. Is that okay?
Wait, but wouldn't it be different because it's d squared now and not just d?
Yeah, so I just put the d over 2 and then squared it.
Yeah, okay, okay,
Okay?
okay.
Just quickly write this down.
Yeah.
Is that clear to you?
Yeah.
Okay, perfect. Hmm. Okay. So in the last class, we talked about the VI graph. So we said that if you put the potential on one axis and current on the other axis, so I'm putting the V, which is in volts, and the I is the current, which is in amperes or the amps. When you draw the line, you see that the because your V is proportional to the I, the graph comes out to be like a straight line like this. Okay. And here, if you find the gradient of this graph, this gradient is will give you the value for resistance. Okay. Let's take an example for this. I'm given with a graph in which V on one side, I on the other side. If I make the graph here and the graph comes out to be like this, the values are given over here. This is 4 amperes and this is 20 volts. So if you find the gradient of this graph, if you want to find the gradient of this graph, that will be giving you the resistance. How much is the gradient of the given graph?
Is it just 5?
Yeah, exactly. It's 20 divided by 4, which is 5 watt.
5, 5 versus 5 ohms.
Yes, that's correct. Got it?
Yeah.
Okay, perfect. The graphs which shows you a straight line, these are called as the ohmic resistance. These are called as the ohmic resistance. So if in a case, so what are ohmic resistance? The graph shows the straight line or the graph which follow the Ohm's law. So in that case, the resistance are called as the ohmic resistance. On the other side, we have another category that's called the non-ohmic resistance, and that's like the non-ohmic resistance is the one which does not follow the straight line, which does not doesn't follow the Ohm's law. Now, if it doesn't follow the Ohm's law, in that case, if you draw the graph between V and I, this is no longer be a straight line. It's always going to be something like this, like a tilt or something like that. Okay.
Okay.
So if it's a straight line, we call it as the ohmic resistance. And if it's not a straight line, maybe a curve, parabola, anything, that's an example of non-ohmic resistance.
Okay.
Is that okay?
Yeah.
Okay, let's move to the next one. For example, if I have a filament lamp, for a filament lamp, if you draw the graph between current and potential difference. So let's say on this axis, I'm having the current, on this axis, I'm having the potential difference. If you draw the graph for filament lamp comes out to be something like this. Now, this is non-ohmic, okay? This is an example of non-ohmic. Even if you do the graph for a diode, if you do a graph for a diode, even that is a non-ohmic for a diode. So that's how it looked like. So diode actually in a circuit, diode looked like this. This is like the positive side of a diode, and that's the negative side, a small triangle with the vertical line. If you draw the graph for this, a diode seems to be like this. And on the reverse side, this way. So this is called as the forward biasing, and that's called as the reverse biasing. You can clearly see that here again, there is no straight line relationship. So that's a non-ohmic resistance. That's another example, the non-ohmic resistance. Okay.
Yeah.
Now, what is a diode? If I give you a very simple example, for example, if you have to charge your phone, how do you charge that? You have to connect with the charger, right? Now,
Yeah.
what is a charger? Charger is a diode that converts, like what current comes to your home? Is it AC or DC?
I don't know.
Okay, just make a guess. Is it alternate current or direct current that comes to your home?
DC.
No, it's AC. Okay. Everywhere we use DC, we hardly use anywhere. DC is not that useful for us. But the problem with the charger, for example, let's say if I have to charge my phone, if I charge with an is okay, what's the difference between AC and DC?
Um,
What's the full form?
AC
AC,
is alternate current
AC is alternate current. Yes.
and DC is diode current.
That's perfect. So can I say that direct current means the current flows in only one direction? But when I say the DC current, the current flows in both the direction. First it flows clockwise, then it flows anti-clockwise. The positive and negative, both the directions, right?
Yeah.
Let's say if I keep my phone on the charging, I directly connect it with the AC source. Now AC, how does it work? First it flows current clockwise, anti-clockwise. The moment you connect it with the charger, first it charge it, charge it, discharge it. So even if you keep your phone in an AC circuit, it won't be able to charge. You won't be able to charge that. But in order to charge it, I need the current in only one direction. So I need what current? I need a DC current. Okay, so that's why if you look at this charger, right? So for example, this is a charger. If you look at inside this charger, we have a diode that converts the AC current into a DC current. So that's a diode. Okay. So if I'm having a direct current or current only in one direction, then only the charging is possible. So if I have to charge my phone, my laptop, my tablet, everywhere I need a DC current. And the current that comes to my house is not AC, it's not DC, it's AC. So I have to put a charger to convert AC into a DC current. Is that okay?
Okay, wait, but why would they need like why do they need to convert it? Is it because they need to like charge it and discharge it and like go both
Otherwise,
directions?
just tell me one thing. For example, I give you $10 and I take you back. I again give you $10. I then again take that $10 back. If I
Yeah.
continue that throughout the day, what will be left with you after the end of the day? Nothing, right?
Zero. Yeah.
Zero. That's what happens in the AC current. Current flows in one direction, charge it. Again, flows in the opposite direction, discharge it. So how do you charge that? It's not
Oh, okay.
possible to charge
And
a
for
battery.
so basically if you were to charge your phone with that, as soon as you take it out, it would get discharged.
Exactly. There's no charging possible in an AC circuit. Exactly the same example, the one I gave it to you. I give you $10 and then I take it back. Again give you 10, then again I take it back. So what is left? There's nothing left. At any point of time you see yourself, there's nothing left to you.
Yeah.
Got it? So, but in DC, that's completely opposite. I'm giving you $10, giving you $10, giving you $10. Now your capital is rising, right? Correct? So
Okay.
DC
Yeah.
is like only one side, and AC is like giving, taking back, giving, taking back. So what current comes to our houses? Is it AC or
AC.
yes? And how do we have to charge for example, if I have to charge a battery, do I need
Yeah.
AC or DC?
DC.
What's wrong with the AC?
Because it like puts the charge and then it takes it out.
Yes, you cannot, at the end of the day, you will be left with nothing. Okay?
Yeah. Yeah.
Is it done so far?
Yeah.
Okay, fine. Hmm. The next we are going to start is the electric power or the work done. Okay, so just imagine if there is a current flowing to the circuit, who is responsible for that? The battery, right? If there is
Yeah.
no battery, there is no current. Agreed?
Yeah.
Okay, so I can say that the battery is the one who is the main power source that runs the circuit. Until and unless the battery is charged, you will be able to run the circuit. The moment the battery is discharged or you remove the battery, you switch off the circuit, there is no current. So what
Yeah.
is done here? In order to move this charge, do I have to do some work?
Um,
In order to move the electrons throughout the circuit, I have to do work, right?
yeah.
Okay, so the work done per unit charge, we call it as the potential difference, correct?
Yeah.
And how much work I have done per unit time, that's your power. How much work is being done by you per second, that's your power. Got it?
Okay.
Now, how do you measure the power? Do you know the unit of power?
Is it joules?
It's joules per second. We call like the work per unit time, the joules per second. In short, we call it as the watts. Okay, like 100 watts,
Okay.
200 watts,
Okay.
not volt, watts. Okay, very
Yeah.
similar sounds. So it's watts. Fine. So now let's see what is left with us now. So we have electric power, electrical energy. That's one topic which is left, the units of it. And then, yeah, this is all left. And then we have a few circuits that we have to do. Okay, so this is what we are left with. So in the next class, we'll be starting with the electrical energy and the power. Okay. Then after that, we'll do the electrical safeties. We'll talk about these diodes and everything in details. Have you done the questions on series and parallel in the last class?
Um, I think so.
Okay. So we will try to do some more questions, some difficult ones in the next class. Okay.
Okay.
Fine then. See you next class. Bye.
Bye bye. Thank you so much.